Hi everyone, and thank you so much for coming to my talk after lunch. I know after lunch can be a bit of a sleepy time, so I'll hopefully have at least a few fun animations to keep you awake. And today I'm going to be talking to you about my work on behavioral priors for specifically tool use and construction. And I'm as already mentioned, I'm pretty inspired by actually just what animals can do in the natural world, because they can do a lot of really complex things, right? So octopuses can do these really cool behaviors where, for example, they can get coconut shells and take them with them across the seafloor to protect themselves from predators. There's these very famous examples of crows that can solve these relatively complicated sort of physical reasoning problems where they have to do things, whatever they can, essentially, to try to get food out of these different tubes of water. And there's also these really classic experiments looking at apes and how they can figure out, again, different kinds of problem solving or construction in order to get out of reach bananas. It's always essentially out of reach food that's motivating in these animal experiments. But most of my research really actually mostly studies humans, in part because humans are able to essentially really one-up animals in terms of the actions that they can do. So we can actually create tools to change the very actions we have access to, right? We can do things like make stone knives to cut things, or even really complex tools like artificial lungs that can let us breathe. And it's not just a small set of humans that can do this. As far as we know, it's all cultures, and it starts pretty young. So here's the first of my fun videos of this child, again, motivated by this out-of-reach food, figures out how to repurpose this tool in a pretty unusual way. It's this shovel, and they're using it to try to get that out-of-reach Easter egg. And of course, they're not perfect here, right? They're efficient in that they figured out the right kind of thing to do, and they're flexible. They try both ends of the tool. They try a variety of different hand positions to try to make this work. They're very persistent in all of the actions they're attempting. Unfortunately, in this case, they're just scooped by a slightly taller child with an unfair height advantage, but I'm sure he'll have his day eventually. And as you might already know, despite a lot of progress, machines aren't quite as good as animals at these kinds of tasks. So there has been a lot of progress, and these are relatively old videos, but I just want to show them as motivation. So on the one hand, we have modern machine learning, where a lot of these modern machine learning techniques try to do away with all of these kinds of abstractions that we think humans have and learn everything that they can from all the data that they can find. And this leads to impressive behaviors. Sorry that I've gone into the dark here, but they're enormously inefficient and they struggle with generalization. And even when we try to create methods that are directly optimized for robustness to these changes, like in meta learning, this flexibility is still generally pretty limited, and the kinds of tasks that we use to test this flexibility are limited as well, like just reaching to a different point on a plane. Now, on the other hand, there's robotics, and roboticists generally like to add more kinds of abstractions to their systems to make the systems more efficient, but this also can lead to brittleness. So in some work that we did in 2018, for example, we got pretty impressive robot manipulation behavior by having these robots that could use these tools in flexible ways, but in very unrealistic ways, because all of the physics here was hard-coded, and this can lead in more extreme cases to these pretty catastrophic failures, like these classic robot fail videos from ages ago. So animals and humans are clearly striking this sort of more interesting balance between these two extremes. We can learn behaviors that we didn't previously know how to do, unlike at least some of these robotic systems, but it doesn't require hundreds or thousands of years, right? In some cases, it requires only 1 or 2 failures to get the right kind of idea. And so my research generally looks at how that sort of very flexible and rapid action learning and planning is possible, especially in these more complex open-ended tasks, things like physical construction, tool creation, and tool use. And my research is trying to answer this question by both studying human behavior and by building machines that can mimic these abilities. And it suggests that the best way to build machines that mimic human behavior is to try to combine learning with these knowledge-based abstractions. And the kinds of abstractions I consider here are those that we believe humans and animals actually use to represent the world. So for example, we believe the world is composed of objects, and we actually know that even extremely young infants understand what these are. And we know that these objects exist in relation to one another in the world. And through some very clever cognitive science experiments, we know that these relations actually govern the ways that people map scenes into shared representations that can enable this very flexible transfer. And finally, we know that these objects obey the laws of physics, which governs how they move through both space and time, and which guides both children and adults' inferences about a lot of everyday phenomena, things like stability. So a prime example of these things coming together is this problem of construction, which is one that I find very motivating. And in part, I'm motivated by this because it's so widespread, right? So birds have to construct nests, but also beavers have to construct massive dams, and humans have constructed massive landscapes or things like skyscrapers. So the first task I'm going to tell you about is called the gluing task, which is a simplification of these ideas, where now we're going to try to figure out how we can stabilize a given tower by applying the minimal amount of glue. So what you're seeing here is a bunch of different problem configurations where the person is trying to apply glue to the contacts. And after they're done, they can press go and they get to see what happens. And the goal is to try to apply as little glue as possible while making sure that the tower remains stable. And what we're going to ask in this project is how good are humans actually at this task? It's not that easy. But if they are reasonably good, can we actually build machines that are as good or better as humans? So if we wanted to build a machine that could accomplish this kind of task, one option would be to use deep reinforcement learning. But in that case, we have to choose a way to represent our problem and how to represent the different kinds of actions we can take. So a common approach would be to take all of our towers, just convert them to images, pass that to some deep network, and just output a vector that tells us which contact points to glue. But this actually has a sort of subtle fatal flaw. Because of how this network is set up, you have to decide all of the possible gluing points at the same time. And this means that if you added a new action, like just simply adding a new block to the tower, you'd have to essentially start training again from scratch. The number of actions in this kind of setup is essentially fixed by the network architecture. So to remedy this problem, we introduced this relational approach to considering the problem of the action space. Now, the central idea here is to change the representation of the tower from an image to a graph now, with each node representing a block and the edges representing their interactions, in this case, places where there are contacts. Now, instead of learning a deep network that maps an entire tower image to an action vector for all of the different contacts, we're going to learn a single network that applies locally to an edge in the graph and can be shared across all of the edges. Then for each edge, we're going to apply that function to determine whether or not to glue it. Now, because you're sharing this function across the edges, any information you learn about one edge can be shared with all of the others. And this now allows you to really easily generalize to new sizes of towers, and it's substantially more data efficient because the function is shared in this much more meaningful, structured way. Now, we call this idea a relational inductive bias for machine learning, and the type of network we use here is called a graph neural network since it operates over graphs. So now we can see how well this approach compares to our human participants compared to these more unstructured methods like multi-layer perceptrons. So we're going to compare three agents, humans, denoted as H here, these unstructured MLPs, and graph networks. And each machine learning method is going to be trained on 100,000 towers of each size, and then tested on 15 held-out towers. Now, what I'm going to show you first is the total reward achieved by each of these different methods, where the total possible reward across the test problems is shown as this dashed line at the top. So if we look at humans, they do kind of okay. They get about half the maximum reward possible, which is not bad considering that they actually only had one tower of each size to train on instead of 100,000. But even despite this, MLPs are a lot worse. I'm not showing it here, but they can solve some of the easier problems, but they completely fail to solve the larger test tower sizes. A lot worse than humans are at this kind of task. But excitingly, these graph networks do a lot better than both. They actually come close to achieving the optimal amount of reward possible across these test problems. So they're surpassing both humans and these unstructured methods. We can also look at generalization by training on just subsets of the data. So in this case, we're going to train one of our networks on just 2 to 6 block tower sizes and 8 to 9 blocks, but leave out 7 and 10, and see how well they generalize to the 7 and 10 block cases. And we're going to compare that to ones that are trained on just all of the different problems, which are shown here in blue. So in orange now, these are the ones that were trained on only a subset of the problems. What you see is that it does just as well. It both gets the 7 blocks and it can even extrapolate to the 10 block case about as well as if it had seen those problems in training, which is cool. This suggests that overall, these relational abstractions of the policy help with both the overall performance, but also the sort of generalization or flexibility of this model, which is better capturing human behavior. So that seems like it's pretty good, but the story doesn't really end there, right? So this was an extremely simplified notion of construction. And I motivated this by talking about skyscrapers or dams or nests. And in order to get to these much higher dimensional problems, we're going to have to move beyond RL, where exploration is now a problem, and we're gonna have to rely on models, right? So we can no longer plan one brick at a time like we did in this gluing task. We might have to use hierarchical kinds of structures or something more fancy. We also can't collect 100,000 examples of skyscrapers. We're really going to need physical models, just like engineers use, in order to try to plan something before we actually build it. So in this next project, I'm going to talk to you about some changes that we've had to make to these systems to get them to work for much higher dimensional problems. And the kind of problem that I'm interested in is this one that we generally call tool creation. So tool creation is actually one of the most complex things animals can do. And other than humans, only a few species of crows are actually known to create tools. And it's hard for a lot of reasons. So we have to have flexibility to new situations, like this crow that's figuring out how to use a stick for the first time to get into this hole that it can't reach. It requires very high dimensional action spaces, like things like creating irrigation systems and totally transforming landscapes to reroute water. And it also requires high precision, like in airplanes where we have to get the exact wing shape very precise in order for that to be a reliable enough tool that people are going to risk their lives to enter. And so in this project, I'm going to explain how we can build machines that can tackle these kinds of tool creation problems by moving beyond reinforcement learning now and taking advantage of both better optimization tools, but also critically physical models. And we're going to look at this for 3 different environments, where our first environment is going to capture sort of simple but very flexible tool creation. Our second environment is going to test these very high dimensional landscape design problems to reroute water. And the third environment is going to test whether these approaches could even potentially help human engineers to design practical tools like airplane wings. So how might we formalize this as a machine learning problem? We're going to start with some initial scene, which I'm denoting here as alpha, which could, for example, be a pipe on the wall from which water is going to flow. We're then going to introduce this design function, FD, which takes in design parameters phi to make the design. And here phi is, for example, the height map of a landscape shown here in green. So these blue and red regions denote the height of this landscape shown in green. And this is going to create an initial graph that we call GT0, which we can simulate then for k time steps. We're then going to calculate reward using FR here with some parameters theta r on the final scene only, where here we want to get the particles into these pink pool regions that are denoted on the floor. Our optimization process is then very simple. It's just going to find the parameters phi that maximize the reward on this simulated scene. And so we start with a random initialization, simulate the scene, and then update these design parameters to increase the reward. But critically, we aren't going to take any more real environment samples through this optimization process. It's going to be entirely done in simulation. So now there could be a lot of options for how we actually simulate the scene and which optimizers we consider for trying to find better and better designs phi. So on the one hand, we have these cases where only black box models are available for the specific domain in terms of describing the simulation procedure. And here, what's been very popular are these sampling-based strategies, similar to those used in model-based reinforcement learning, such as the cross-entropy method. And these are among sort of the most commonly used optimizers. On the other end of the spectrum, very engineered, we have these engineering-based models, where usually a set of experts derives very precise analytical systems for the design task at hand, and whose derivatives can be used to perform precise gradient-based optimization. Now, our main interest was to try to see if we could look between these two extremes. We want to leverage these gradient-based optimization methods for inverse design, but on these much more flexible, general purpose, learned and differentiable models. And we're going to use graph networks here again, just like I showed you before. But now, instead of each block being a node, each particle is going to be a node within like these fluid design systems or within the mesh. And now the edges in that graph are going to connect nearby particles so that they can transmit information. And instead of predicting whether to glue two blocks together, we're going to predict the updated positions of all of the particles in the graph. Now, what's cool is that these graph networks do work really well for physics prediction. They can really operate over hundreds to thousands of particles, and they're differential because they're parameterized as neural networks. But more importantly for us, they also generalize. So for example, the training domains here you can see are very simplified single tool segments where a giant block of water is falling onto that, and then they can generalize to these much more complex multi-segment kinds of scenes, which is exciting. And so our question is, can we use these pre-trained graph neural network models trained in these simplified domains to be able and use them to create tools like this, where we have a much smaller number of particles, the actual shape of the tool is totally different than what we saw during training, and essentially completely a task agnostic approach to inverse design. And the real question is here whether or not these graph networks are going to yield useful enough gradients for us to be able to actually optimize tool designs that can be outside of these training distributions. So now let's look at some results. So our simplest task here is this 2D fluid environment where the goal is to bring the fluid as close as possible to this yellow region and keep it there in the center. And this task is still fairly complex. It contains between 100 and 1,000 particles to be simulated and between 16 and 36 design dimensions to optimize. And what I'm showing you here is the optimization traces for this gradient-based design optimization procedure, where we can see that with this pre-trained GNN model, it's able to very effectively refine the shapes of these tools to make things like containers, ramps, and even these pretty complex sorts of funnels in order to get the fluid into these yellow regions. If we compare that to how one of these classic sampling-based optimization procedures works, like CEM, it's generating shapes that are much more jagged and, in the case of this maze example down here, for example, very globally incoherent, which just seems a lot less human-like in terms of the kinds of things that it's able to come up with. Now, unsurprisingly, based on these examples, it seems like the gradient-based method is performing a lot better across these different tasks if we look at the total reward that it achieves. But these are both with the simulated model. And one thing you could argue is that, well, the sampling-based method, you could just use the ground truth. You don't need to use the graph neural network model at all. And if you do that, you do better, but you actually still don't perform as well as if you use the gradient-based optimization procedure with these learned models. And these are all evaluated using the true simulator. So there's something very powerful about the gradients that allows you to just find better regions of the space in order to create better tools. So we then wanted to really test the scalability of this approach. So we moved to this 3D domain with now 2,000 to 4,000 particles and 625 design dimensions, so way larger spaces. And the goal of the task here is to optimize this height field of the landscape, shown in green, to move the water, which is blue, into these pink pools. And here, the gradient-based method outperforms the sampling-based CEM method by actually 1 to 2 orders of magnitude. And if you look at these examples, it's pretty easy to see how, right? Crafting these landscapes requires these globally coherent designs across a very large number of design parameters. And what's also cool about this method is that it's precise enough to allow us to solve pretty legitimate problems for engineering, where precision is key and lots of work has gone into making these highly specialized tools, like this classic problem of designing an airfoil wing. So here, the goal is to find an airfoil shape with minimum drag under a constant lift. And what we're really excited about here is that we're able to discover airfoil wings that obtain comparable reward to this specialized defoam solver, which is highly specialized for this type of design, while using a much more generic method of gradient descent on these learned simulator models, which is just pre-trained on random wing configurations. So let me show you examples of that. So this is the defoam solution to the problem, where the blue areas are regions of low pressure and the yellow areas are regions of high pressure. So the high pressure is going to move this plane up and it has minimal drag. If you use a single graph neural network model, you do a pretty good job, but still not achieving quite the same reward as the defoam model. But if you simply just use an ensemble of 5 models, you're actually able to get to exactly the same reward as this defoam approach, which is quite encouraging. And even at the ensemble size of 5 here, this generic gradient descent approach with the learned differentiable model is still 16 to 48 times faster than the specialized defoam solution. And so across all 3 of these domains, differentiable physical models were key to success and key to performing well in both high dimensions in the state and high dimensions in the action space. So to wrap up, I presented a few different kinds of behavioral abstractions for humans and how they impact both human and machine physical reasoning. Relational abstractions over policies support things like construction capabilities, both in overall reward and in flexibility. These relational policies weren't enough for being able to support more complex tasks like tool creation. And that seemed to also require physics and fancier forms of gradient-based optimization. And although I didn't talk about it today, my PhD thesis explored tool use by humans and machines, which we found was supported by not just relational action representations, nor just physics, but instead both. It requires both differentiable physical models and these relational representations for things like RL, which I could talk about if people are curious at some other point. So just that's it for me. A quick thank you to my wonderful collaborators, both at DeepMind and at MIT, and to all of you in the audience for listening, and of course to the organizers for having me. If you're curious about any of these projects, you can check out my website, and I'm happy to take any questions if there's time.
Thank you so much, Kelsey. Let's have a round of applause. Yeah, I guess the floor is open for any questions. Yes, we have a question here at the end.
How realistic is simulating fluids with individual particles, even thousands of particles, in the real world? Is that the goal to eventually do that?
Kelsey, were you able to hear the question? Kelsey, hello?
I can't hear anything at all. Sorry. I think I might have had something muted. Can that please be repeated? My deepest apologies.
Yeah, no worries. Do you hear us now?
Yes, I can hear you now.
Yeah, my question was, how realistic is to simulate liquid into using thousands of particles? How realistic is it? Is the goal to eventually do this in the real world? And how well will that transfer?
Yeah, it's a great question. So that's something that we're actively looking at. I think in order to generalize to the real world, the real missing thing about what I presented is vision. So it's going to be hard all of the methods that I presented today depend on having an accurate representation of the state. And so in order to be able to do sim to real transfer here, we would need to be able to make these methods work from vision. But there's been quite a lot of exciting work doing that relatively recently from places like NVIDIA that have shown that you can take vision-based representations and put them into graph-based formats. And so I think if you can do that, I would expect these kinds of simulators to actually generalize to the real world better than those that are hand-coded, because we could potentially fine-tune them with real-world data, for example, in a way that you couldn't if you were to write all those things down analytically.
Any other questions?
I've got one. Can I go ahead?
Yeah, go ahead.
So Kelsey, thanks for a great talk. I had a question that may not be directly related to the work you just presented, but there was something you mentioned about using these graph networks to allow for different dimensional action spaces. And I thought that would be quite interesting in an RL perspective, where we want to have like a very general policy that can work across different robot morphologies. Is that something that you've explored with these graph networks in your particular work? Like just how, like try to build a very general agent?
So that's something we are actively exploring. There's also been a ton of really cool work on this from people like Deepak Pathak, where they've done generic body morphologies with graph neural networks that even can change in real time and learn to control those using RL. And actually some of the earliest work was on this as well, a paper called NerveNet that tried to represent robot bodies as graphs with different edges edge types given by different joint types. And they also showed some kind of cool robot morphology generalization. So I think it's a really promising area, and it's something that I think would be really cool to come back to, especially because now we might be able to use like the gradients of those models to do even higher dimensional optimization or change the shapes or something like that of the different aspects of the body.
Yeah. Thank you.
I think that's all the questions from here, unless there are any online.
Could I ask a question? Can you hear me?
Yes, please go ahead.
Yeah. So thank you for your presentation, and I'm curious about how the fluid dynamics model of the water is trained using graph neural networks. So, like, based on the image, is the relation between the water particles are trained? So, like, how is it?
Yeah. So let me go back a few slides. So so the big question that you're asking is like, what is the representation of this FM with respect to these water scenes, right?
Yes, it's right.
Yeah. So the way you should think about this is that each one of these little nodes in white corresponds to a different particle in the scene. These can have two different types, either a fluid type, which is the blue particles here, or they can have a solid type, which is like all of the green particles that make up the mesh. The edges are then defined as just existing between all particles within a certain, what we call connectivity radius. So that connectivity radius could specify that any particles within like, 10 centimeters or something will be connected. And that's just to allow nearby particles to communicate, since if they're, in contact or trying to like under high pressure, then they need to be able to communicate with their immediate neighbors so that the state evolution can proceed as expected. So we don't learn this edge connectivity. It's all determined by just how close the particles are to each other as predicted by the graph network. Does that make sense?
So you mean by like it's more about not about learning the graph, learning the connection, but it's about like how close they should be to have an effect on each particles, like any particles, yeah.
Yeah, so that's how the graph is represented. And then what we learn is functions that take in a node representation and an edge representation, and the node like the two nodes that are connected by the edge as well as that edge. And we're going to pass those through to an MLP, and that's going to give us updated representations for the nodes and the edges and the other nodes. And we're going to try to use that to figure out how to predict the next time step. So what we're learning is representations of the graph, or representations of the nodes and the edges that allows us to make a next state prediction effectively. But we're not learning the connectivity of the graph.
Yeah, thank you very much for your question. Answer. Thank you.
Thanks for asking.
That's all the time we have for questions. Thanks once again, Kelsey, for that incredible talk.